we're going to work on a problem in Connect that was created with a static problem set. Sorry about that, I had to go get the right problem. We're going to be working on an assembly line balancing problem, and basically problem 6.8 in Connect says the desired daily output for an assembly line is 360 units. This assembly line wants to operate 450 minutes per day, and the following table contains information on this product's task times and precedence relationships. Okay, with that information, I'm going to go ahead and open up a new Excel file. Actually, I'll probably use an old one here and just switch to a different tab. All right, and I'm going to copy and paste in the information from Excel, and I'm going to use that table. I'm going to copy, I'm going to go back to Excel, and I'm going to paste special text. And I'm just going to clean this up a little bit, give myself a little bit more space, wrap the text on those. Center these columns. All right, and then I'm going to come back just because I can, and I'm going to go ahead and get the information. I'm going to close this one so I quit looking at it accidentally. And I'm going to come back here, and I'm going to grab this information regarding the desired daily output, and we'll copy and paste that into our file. Kind of a mess the way that went in, but we'll get her so we can see it here. And I'll left justify that. Okay, so there's the information that we're taking from Excel to copy into our that we're taking from Canvas to copy into our problem. Today we're going to take a look at problem 6.8. This is a static problem that was created in Connect, and it's going to be similar to some of your homework problems. It's about assembly line balancing, and so I wanted to go ahead and start by using Excel to go ahead and solve this problem. So I want to take the data that we've got here, and I'm going to copy it into Excel. I'm going to go paste special text, and I'm going to go ahead and clean up the copy paste process just a little bit. We'll wrap the text on those two cells. We'll center up these, right? And we'll come back and we'll make sure that we have the information that we want, which is the desired daily output is 360 units, and the assembly line will operate 450 minutes per day. So desired output, assembly line operates 450 minutes per each day. Okay, so with that information, we're going to go ahead and look at I'm not sure why my Excel stopped and restarted, but it did. But with that in, what we're going to do is we're going to go ahead and move that over to the left so that we can read everything. Okay, and I'm going to go ahead and take a look then and say, okay, we're going to take a look at problem 6.8 from Connect, and it's an assembly line balancing problem. I've gone ahead and set up a spreadsheet here in Excel that has that information on it. So you can see that I've transferred in the tasks, the task time, which is how much time it takes in seconds to do each one of these tasks. So you could think about a task might be, if you were on an assembly line making a bicycle, maybe the task is putting, farther down the line here, maybe this task is actually putting the bicycle seat onto the frame, right? And that task takes so much time. All right, and so then the precedence diagram, or this tells us what has to go, in what sequence things have to go together. For example, you couldn't put the wheels on the frame before you've welded the frame together. And so if you think about those tasks, some tasks have to be done in a particular sequence. And that's what this little chart tells us. From the problem, it also told us that our desired output was 360 units per day, and that the assembly line operates 450 minutes each day. If you were to look in your text on pages basically 186, 187, and 188, there's a very similar example to this. And we're going to use that as kind of our basis for how we're going to work this problem. And so the first thing that we want to do is we want to draw the precedence diagram. Okay? And so when we draw the precedence diagram, we look at this information and we figure out what sequence things need to be done in. Okay? And so basically I can tell by looking at this that task A doesn't have any predecessors, so it can go all the way to the left of my chart. And when I do this, I go ahead and type in the seconds next to that because I'm going to use that later on. Okay? And then I can tell that task B follows task A, and it has a 35-second task time. And I can tell that task C also follows task A, and it has a 30-second task time. Okay? Then it tells me that task D follows task B, and it has a 35-second task time. E follows C, and it has a 15-second task time. And F also follows C, and it has a 65-second task time. And then G follows E and F with a 40-second task time. And H follows D and G with a 25-second task time. So that the way this is laid out doesn't tell us much yet, but what I want to do is go ahead and insert arrows to kind of show those relationships. And basically I'm going to need 1, 2, 3, 4, 5, 6, 7. I think I'm going to need about 8 arrows. So I'm going to copy and paste that 8 times. Okay. And so then I'm going to take those arrows and I'm going to go ahead and move them to where they need to be. So A going to B, A going to C, and I actually want to capture the end and move the end only. B going to D, C going to E, C going to F, D going to H, E going to G, F going to G, and I need one more of those arrows, and G going to H. Oops. Okay, so there's my precedence diagram. The second thing that I need to do in this type of a problem is I need to determine the required workstation cycle time using the formula of production time per day divided by, let me go ahead and fix that spelling error, required output per day. Okay, so that being said, I know that my production time per day is 450 minutes. And I know that my desired output is 360 units. Okay? However, if I'm thoughtful about this, I would probably look at this question to see that my workstation cycle time has to be given in seconds. So basically, I want to make sure that when I calculate this out, that I calculate it out in seconds. And so I need to convert my 450 minutes to seconds. So in my numerator, it's going to be 450 minutes times 60 seconds per minute, right? And then I'm going to divide that by my 360 units, and that's going to give me my cycle time of 75 seconds. And just because you may need a little further information about how that was calculated, I'll go ahead and put kind of the working it out in a little longer sequence there. But here's my cycle time, 75 seconds. Okay. The third thing that I need to do is I need to determine the theoretical number of workstations. And if I'm going to determine the theoretical number of workstations, I'm going to use the formula that n is equal to the sum of the task times divided by the cycle times. Okay, so again, I'm going to use the formula n is equal to the sum of the task time divided by the cycle time. All right, so I need to have the sum of my task times. So I'm going to sum up those task times, and that's 275 seconds. So the theoretical number of workstations says it's going to be 275 divided by my cycle time of 75 seconds, which says it would be 3.667, okay, theoretical workstations, meaning in the best case scenario, that's how many I could get away with. But you can't have 0.67 of a workstation, so you round up to 4 whole workstations, okay? And again, that's saying in the best case scenario, that's the fewest number of workstations that I could have, all right? And then the next thing that we want to do is we want to go ahead and we want to balance the line using the largest number of following tasks, and then use the longest task time as a secondary criterion, okay? Well, when we do that, and basically the textbook lays that rule out, and it says select a primary rule by which tasks are to be assigned to workstations and a secondary rule to break ties. Well, if you go into Connect, this is going to be the rule that they tell us, right? So if I come back to Connect, it's going to say balance this line using the largest number of following tasks, use the longest task time as a secondary criterion, which is exactly what we've listed here, okay? And so what that means to us is I'm going to look at these tasks and I'm going to try to combine them up in a way that none of the workstations that we combine up tasks for exceed 75 seconds. And you think about this as if on our bicycle production line, maybe at one workstation we weld the frame together, maybe at the second workstation we do 2 tasks where we put the handlebars on and we put the seat on, right? And so again, what we're looking here is at these individual tasks and how we want to combine them up on the assembly line. And the bottom line is that you can't combine A and H together, because in this precedence diagram, everything in the middle has to be done before we can get to H. So we usually start from left to right, and again, we're using the largest number of following tasks. So I would look at left, I would have A has to be done, and then I can look at B and C. Well, C clearly has more following tasks than B, so I would combine A and C together to begin with, and that's 30 seconds, and then I'd go on and say, so clearly I can't do F, but I could put E in there because it's 15 seconds, and so that workstation is going to sum to 75 seconds. Okay? And then I'd look at the second option I had, and I'm again going by largest number of following tasks. Okay, well, F has 2 following tasks, E has 2 following tasks, and D has 2 following tasks. So I have some ties here. To break the tie, I use the longest task time, which brings me to F. And F can't be combined up with anything. It really has to be on its own, okay? Because if I tried to add 40 seconds to that, it's going to exceed the cycle time that we can have at any given workstation, right? Then I'm going to come back to B, and I'm going to look at B and D, right? Do I want to combine them up, or do I want to combine B and G up? Well, each of them only has 1 task following, but then according to our rule, we break the tie by which one has the longest task time. So then G has the longest task time, and so that workstation has a cycle time of 75 seconds, and then I finish up with my last 2 tasks, D and H, and I sum them together. Okay, so then if I were going to kind of make this a little simpler, what we do is we'd say our workstations consist of the following tasks and then the following time at each workstation. Okay, so workstation 1 has tasks A, C, and E, and if I sum up the time at that workstation, 30 plus 30 plus 15 is 75 seconds. Workstation 2 is task F only, and it has a task time of 65 seconds at it. Workstation 3 is going to be task B and G, and those summed together have a time of 75 seconds. And Workstation 4 is D and H, and those summed together have a time of 60 seconds. Okay. In your problem, you're also asked to let them know what the idle time is at each workstation. Okay. If our cycle time is 75 seconds at each workstation, our idle time is the cycle time, what we're allotted at each workstation, minus the actual time it takes us to do the tasks. Okay. And so again, in the first workstation, we have 0 idle time. In the second, we have 10 seconds. In the third, we have 0. And in the fourth, we have 15. Okay. So that takes us through step number 4. Step number 5 says I need to calculate the efficiency at that particular assembly line based on this layout. And I do that by taking the sum of the task times, so our 275, and I divide it by the actual number of workstations. So let's come up and count. We've got 4 workstations times our cycle time of 75 seconds. And then I'm going to multiply it by 100 because we're going to answer in a percentage. Okay, and I'm going to go ahead and decrease that to 2 decimal points. That gives us 91.67%. Okay, with that being said, we can look at our solution here, and we can see that our cycle time was 75 seconds. We can see that our workstations ACE matches. We have 0 idle time. F with 10 seconds of idle time. Workstation 3 is B and G with 0 idle time. Workstation 4 is D and H with 15 seconds of idle time. And last but not least, we have 91.67% for our efficiency, but we're within the range of error of 0.05%. So good luck with those problems in Connect. Again, if you need a different review, you can go back to your textbook and you can look at pages 186, 187, and 188 in your textbook. And again, I wish you the best of luck.